Can you respond if you can hear me?
Yes, Prof. How are you doing?
I'm doing well. I was just wondering that a number of you have not joined yet, but we have to start. Yeah, so that they learn to keep time. You need to confirm to me whether my presentation is visible at your end.
Yes, Prof, we can see you.
Thank you very well. The presentation, I mean. Yeah.
Yes.
So we start from where we left last time. Uh, After we discussed the probability and its properties, we stopped at conditional probabilities. And then another important aspect in probability theory is that of independence. And this is a very important aspect in the sense that we shall see also how it is applied to random variables later on. And even the idea of conditional probability would be also applied to random variables. And then you can see when we were discussing random samples, we're talking about independent, you know, independent or a random sample where you see we're using conditionals, and then we shall see what happens when you talk about independence. So it's actually a consequence which comes from actually conditional probability. So first and foremost, we shall start with two events, and then we shall extend to an arbitrary number, say k, uh, as far as dependence is concerned. So events, so you can see my made my cursor very big so that when I point, I made my cursor very big so when I point it is green in color. When I point
Excuse
you
me,
are
Prof.
hello.
Hello, sorry for interrupting.
Mm.
There's someone waiting to be let in. You could.
I don't know why some people are able to join and others are not. What could be the problem?
I think they're using the email switch, probably a different email from the one that is in the list of emails that you have.
They usually recommend that you use the one which is sent as an invite. Because
Yeah.
I'm trying to, there's somebody says wants to join. When I click, nothing happens. And
Or
what
you
is wrong
can.
with the email? Eh?
Okay. Yeah.
Yeah.
You can also make me a co-host so that I
Mm.
can add them to minimize
I'm also asking,
interruption. Yeah.
I should not be anticipating any interruption in the sense that why can somebody use the email which he or she provided for the class? I
For
know we have a
example,
multiplicity of emails.
yeah.
Yeah.
For
And then we
example,
usually recommend,
yeah. Sorry. You
we
can
usually,
go ahead.
we usually recommend
Yeah.
that you use your own emails.
Okay.
Even me, I have a Gmail and I have your own email. And for visual matters, usually
Yeah.
even classes, usually it's advisable you use your own emails. So that's people
Okay.
not just using their social media things.
Yeah.
So this person, I don't know, as in this person I did at any class before.
Yeah.
Which
It's
email
part
was he
of
using?
us. Yeah.
Which email was he using? Which one?
I'm not very sure.
Because because even in the past I've not been admitting anyone. They just enter. Hmm?
Maybe he has switched to a personal email or something. I'm not very sure.
They
But
should
it's
not
part of
switch.
us.
They should not switch. Hmm? Because this is a regular class. Hmm?
Mm.
So if we task you to be admitting them, that is saying they either what could be the explanation that they are not able to join, that somebody else has to admit them. No, that is doing too much for someone, isn't
Yeah.
it? Yeah, yeah. They should take responsibility. So we are going to start.
Okay.
Uh, advise them to use the email which they have sent for invite. Okay, because if they use that email, because I've indicated invite all and I've said admit all. Okay.
Mm.
So they should, I don't anticipate any problem. It's only them who are they are living randomly. They do things randomly. Sawa.
Sawa.
So let's proceed. So here I indicated that we are going to start on a very important concept called independence, and we are just defining. Uh, and I said we are going to start with two events, and then we extend it to an arbitrary number of events, which is always the general case, and also what happens in practice. We only don't deal with two events. So events E1 and E2 in a sample space S are said to be statistically independent even only if the probability that they occur together is the product. You can see when you are talking about axioms, when you are talking about probability of the union of events, you are saying you sum them when they are mutually exclusive. So you can see the union, the interpretation is that at least one of them occurs. But for the intersection, both of them occur. So the probability that the two events occur simultaneously is basically the product of the probabilities. As simple as that. That is how independence is defined, and we shall see in a moment what that means. If you remember the multiplication theorem, which actually gives us the probability of a simultaneous occurrence of events, which is the probability of the intersection, we're able to compute it using a conditional probability and an absolute probability. So we could be saying probability of E1 dash on E2, we could say it is probability of E1 given E2 times probability of E1. That is, even you are using conditional probability. That is actually a multiplication theorem. Probability of E1 dash on E2, if you remember, is probability of E1 given E2 times probability of E2. And also we can also say probability of E2 given E1 times probability of E1. That is a multiplication theorem. So if the probability of a simultaneous occurrence of two events is the product, it actually means the conditional probability of E1 given E2 is actually probability of E1. This could have been a conditional probability using multiplication theorem. With multiplication theorem, this should be probability of E1 given E2. But this one is equal to probability of E1. So that is why, so that it becomes a product. And in that definition of conditional probability, in the probability theorem, probability of E2 should be positive, meaning the event E2 cannot be an impossible event. Also, we could also have written this as probability of E2 given E1 times probability of E1. That means now this probability of E2 given E1 is probability of E2. In that sense, probability of E1 should be positive, meaning E1 should also not be an impossible event. So when you are so we are actually saying probability of E1 is positive, probability of T2 is positive. So in this definition, we are saying in this product, both of them should be positive for this to be well defined. Probability of E1 should be positive, probability of E2 should be positive. In other words, the two events we are asserting to be independent should not be impossible events. Should not be impossible events. Thus, E1 and E2 are independent. So here also let me state this. Usually when you talk of independence, it is in the statistical sense. So this independence is in the statistical sense. Later on, we might leave out the word statistical, whatever, but in our minds should be very clear that the independence we are talking about is statistical in nature. There are various in terms of usage of the word independence, but now in the statistical sense. Does E1, so when I say does E1 and E2 are independent, so you say I've basically truncated statistically independent, but in that understanding that we are referring to the statistical independence. So does E1 and E2 are independent if knowledge of the occurrence of either one of them in no way influence the probability of occurrence of the other. You can actually see like this one. Probability of E1 given E2 is probability of E1. So the occurrence of E2 does not influence the occurrence of E1. Because whether E2 occurs or not doesn't matter. Probability of E1 given E2 is just probability of E1. So occurrence of E1 is not influenced by E2, or also you can say probability of E2 given E1 is probability of E2, meaning the occurrence of E2 is not influenced by E1. That's why we are saying E1 and E2 are independent if knowledge of the occurrence of either one of them in no way influence the probability of occurrence of the other. Yeah. So you get it, the conditional probability is just an ordinary probability. Now, I'll use this example. We had used it also in conditional, but now in under the concept of independence. We had used this example before. Consider the lot of items consisting of 80 non-defective and 20 defective, and you select 2 items at random with replacement. Let E1, the first item is defective. We had defined this even earlier. E2, the second item is defective. Then you can actually see that probability of E1 is equal to probability of E2 is 20 over 100, which is a fifth. Then if probability that the first item is defective is equal to probability that the second item is defective. Also here, which is with replacement. So at any instant, when you are drawing an item, you all the time have 20 defective items in the lot of 100. So you can actually see that is, so we are actually saying probability of E2 given E1 is probability of E2. This independence. And therefore, probability of E1 dash E2 is just the product. So 1 over 5 times 1 over 5 is 1 over 25. All right. There's an early example to explain independence. Actually, the occurrence of E2 is not influenced by the occurrence of E1 because it's with replacement. Because at any instant you are drawing, you have 20 defective items in the lot. So there's independence here. Here's another example. Consider a box containing 4 eggs, of which 2 are bad and 2 eggs are deselected at random from the carton with replacement. This now with replacement. With replacement. We discussed similar idea before, but we were not talking about it was without replacement. We want to define 2 events. E1B to denote the first egg is bad. When you are drawing, the first egg is bad, and then E2B to second egg is bad. Designate bad eggs as 1, 2, and good eggs as 3, 4 as before. So because we are drawing a sample with from the 2 eggs from the carton containing 4 eggs at random with replacement, that is a sample space. We had seen this before. That is the sample space. 1, 2, 3, 4. 1, 2, 3, 4. 4 times 4, 16 sample points as before. You can refer to the earlier notes. And if you define the event 1B, which says the first egg is bad, you can actually track where we have the red, marked red, is where we have a bad egg because we have designated 1 and 2 as bad and 3 and 4 as good. So if you track where the first egg is bad is where we have the first, say in that pair, the first draw as red, we have. So you have the first egg is bad. So the first one is red. And the second one says the second egg is bad. So this one, the second one, the second row must be red. So you can pick the sample points in as described by event 1B and And also the sample points as described by event 2B is indicated. So we have it in 1B, 1, 2, 3, 4, 5, 6, 7, 8. Also we have in event 2B 8 sample points, 8, 8. And if you check the intersection, those which are common, like this 1, 1, 1, 1 is here, so it's 1, 1. You check also 1, 2 is here, 1, 2 is here, also there. 2, 1 is here, 2, 1 is here, okay. 2, 2 is here, also 2, 2 is here, and no other. Those are the points, sample points which are shared. Now, probability of event 1B is equal to probability of 2B. You just count the number of, remember classical definition, the number of points in the event divided by the number of points in the sample space. So each one has 8, so it will be 8 over 60, so it's a half. Probability of each of the two events is a half, they have equal probability. If you check the probability of the intersection, there are 4 sample points. So it should be 4 out of 16 is a quarter. So you can actually see that probability of the intersection is a quarter, which is actually the product of the two probabilities, because it is a half and a half. Actually, these two events are independent. The two events we have defined here are independent. As demonstrated, that actually the probability of the intersection is the product of their probabilities. It means occurrence of one of them is not influenced by knowledge of occurrence of the other. We want to look at immediate consequences of independent events. Yes, we have defined two events being independent. We want to see immediate consequences of this. 1, if E1 and E2 are independent, then E1 complement and E2 are independent. That means if E1 and E2 are independent, it means the complement of E1 and E2 are independent. So it actually means the probability of E1 complement dash E2 should be the product of the probabilities. Should actually be probability of E1 complement times probability of E2. All right. So this is what we need to prove. This is what we need to, so we need to show this. So we start by saying, express E2 as a union of mutually exclusive events. We had done similar things before. So actually we are saying, E2 is in S, the sample space. So E2 is S induction E2. E2 is S induction E2 because E2 is in S. Express S as a union, express S as a union of two mutually exclusive events. But we know E1 complement and E1 are mutually exclusive. So E1 complement union E1 is actually S. Actually, they partition S. So if you do that, so intersect with E2 and then you use distributive law, because intersection distributes over union, you get E1 complement intersection E2 union E1 intersection E2. So the two events, this event and this event are mutually exclusive. They are because E1 complement and E1 are mutually exclusive. Because E1 complement and E1 cannot occur together, these two events cannot occur together, so they are mutually exclusive. So if I want to find, because we have expressed E2 as a union of mutually exclusive events, then we can invoke axiom number 3, the additive rule or finite additivity. So the probability of E2 will just be the sum of probabilities of the mutually exclusive events, which is the right-hand side. Make this the subject, because actually that is our interest. We want to, you can see on the left-hand side, what we want is probability of E1 complement on E2. So make it the subject here. So make it the subject. So it will be probability of E2 minus probability of E1 dash E2. This is the result now, this line here. But you see here, what was indicated was that E1 and E2 are independent. independence. So it's by the definition, we are invoking independence here now. Probability of simultaneous occurrence of E1 and E2 is the product of probabilities. No? So what was defined as independence. So we invoke it there. So we are invoking independence here. So put the product for that. You can see that probability of E2 is common, factorized. Factorize. So you have 1 minus probability of E1 times probability of E2. Factorize out probability of E2. So this is the result. But you can see what you have here using complementation. 1 minus probability of E1 is actually probability of E1 complement. And we are done. So basically, by what it actually means that E1 complement and E2 are independent. Good. Probability of simultaneous occurrence of E1 complement and E2 is a product of the probabilities. Let us see this remark. When we define earlier, we go back very far. We defined earlier here. We defined using that definition here that when they are independent, probability of E1 given E2 is E1. Probability of E2 given E1 is the probability of E2. Let us see when you even bring the complement of events in this remark here. So it actually means probability of, already it was indicated that E1 and E2 are independent. It means probability of E2 given E1 is probability of E2 because E1 and E2 are independent. That means also if you wanted to compute this probability of E1 complement as in E2, you are going to use probability of E2 given probability of E1 complement times probability of E1 complement. So what actually means, this probability of E2 is actually probability of E2 given E1 complement. So probability of E2 given E1 complement is probability of E2. So what actually means is, earlier we said knowledge of occurrence of E1, the probability of the knowledge of occurrence of E2 does not influence the probability of occurrence of E2. Knowledge of occurrence of E1 does not influence the occurrence of E2. And you can see now, because what we deduce from here, this is what we had earlier. So what we deduce from here is that knowledge of non-occurrence, you see, knowledge of non-occurrence of E1 does not influence the occurrence of E2. So whether the event occurs, the events are independent. So whether the event occurs or not, it not influence the other one. With knowledge of occurrence and non-occurrence. So implies probability of occurrence of E2 is not influenced by knowledge of the occurrence, which is actually here, or non-occurrence, which is here, of E1. So whether E1 occurs or doesn't occur, does not influence the event E2. Does not influence the occurrence of that event, or the probability of occurrence, to be more precise. So when we say in this immediate, when we say if E1 and E2 are independent, then E1 complement and E2 complement and E2 are independent. It means this, that if two events are independent, then the complement of one is independent with the other event. It doesn't matter which event you call E1 and which one you call E2. Once you have defined E2 events, just know E1 complement is independent of E2. Then also it also means E2 complement is independent of E1. Well, it doesn't matter which event you call E1. These are just naming for purposes of explanation. Now, another immediate consequence. If E1 and E2 are independent, then their complements are also independent. If E1 and E2 are independent, also their complements are independent. So we need to show this. Probability of E1 complement, induction of E2 complement should be the product of the probabilities, namely probability of E1 complement and probability of E2 complement. All right. So we need to show this. This is what we need to show as before. So you can see what we are using to exactly by definition. That's what we said earlier. If two events are dependent, the probability of the simulated occurrence of the two events should be the product. So this we need to show this. So if we show this, we will approve that E1 complement and E2 complement are independent. So the proof follows. So we want to determine what is probability of E1 complement induction E2 complement. We want to show that it's a product. So we start by saying we invoke De Morgan's law. We know that where De Morgan law says the intersection of complements is the complement of their union. This is De Morgan law. Intersection of complements is actually the complement of their union. That is De Morgan law. So probability. So this is a intersection of complements. This is complement of their union. Yeah. And what I'm invoking here is the rule of complementation. Probability of a complement of an event is 1 minus probability of the event. So the event in question here is E1 union E2. So it will be 1 minus probability of that event, which is E1 union E2. Complementation. There's a reason for each step here. As I indicated, these things you don't gram them. Mathematics is not meant for gramming. It is this by understanding what we call the logical steps. The logical mathematical steps. So they are packed by, you can see what I indicate on the right hand side. So you can see if I go to line 3, we want the probability of a union of two events. We had property 2. We go to property 2 when you are looking at probabilities. So we invoke probability of a union is sum of probabilities minus probability of their intersection. Step number 4 or line 4, I'm now invoking independence because E1 and E2 are independent. I'm invoking here. You can see I'm now saying this probability of the intersection is the product. So I'm invoking independence. The rest now is just to simplify, factorize. This line 4 is factorizable as 1 minus probability of E1 times 1 minus probability of E2. If you expand this, you will get that. It's factorizable. So this is a mathematical, usual mathematical step of factorization. And the last one is the result, because by invoking complementation, you get the result. By invoking complementation, you get the result, because this probability, this 1 minus probability of E1 is what is actually probability of E1 complement, similarly for the other one. You can now see, as far as independence is concerned, what this means actually in this remark is that probability of E1 complement given E2 complement is probability of E1 complement. And probability of E2 complement given E1 complement is just probability of E2 complement. So when events are independent, even their complements are also independent. Now, we want to bring to a particular situation that's to bring out this concept of the independence to be more clear, to be clearer. The tosses of a coin are actually independent. The tosses of a coin are independent. So when you are tossing a coin, say you make the first toss and then you make the second toss. Actually, and then you define events. You find that when you are making the second toss, does not really depend on what occurred in the first toss. So the tosses of so I'm stating that the tosses of a coin are independent. So in particular, consider 2 tosses of a coin so that we have a small sample space. We have used this sample space before. We want to consider 2 cases. One, when the coin is fair, or we say it's unbiased, or we say this is balanced. All right. We want to look at that case. So the sample points in S are equally likely. We had defined this, so we know the classical definition. So probability of each sample point is a quarter. So then we know. Okay. The probability of each sample point is a quarter. These are sample points. Now when you write, say these are now what we can designate as E1, E2, E3, E4, lowercase. But as a sample point, this is a sample point, HH. This is just notation to denote head, 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 tail, head, tail. 4 sample points. So probability of each one of them is a quarter, 1/4. Now, if we look at the tosses, when you write HH, we are saying head on first toss, head on second toss. When you write HT, head on first toss, tail on second toss. And that sample point is different from tail on first toss and head on second toss. So those are different sample points. Then we have tail on first toss and tail on second toss are very different. So that's where you have those 4 sample points. So let us look at each one of them. Actually, probability, we want to find the probability that we have head on first toss and also head on second toss. That's what we mean by simultaneous occurrence of we are saying head occurs on first toss and also head occurs on second toss. You will actually see that because this coin is fair, probability of head is equal to probability of tail is a half. In that, when you toss a coin, in that sample space, we have head and tail. Sample space having 2 sample points, head and tail. And then probability of each one of them is a half, 1/2. One sample point in H is 1/2. 2 is the number of sample points in sample space because there are 2, head and tail. But when you toss it twice, this is a sample space. Because we can also toss, if we toss it 3 times, we'll have 8, like that. Now, so if we look at that, you can actually see that because probability of H equals probability of T is a half, and the probability of each of these sample points when you have for the 2 tosses is a quarter, you can actually see that probability of HH is probability of H times probability of H. Because the ones on the left-hand side, all of them are equal to a quarter. You look at all these sample points, they are all equal to a quarter. And on the right-hand side, they can actually be expressed as a product of the probabilities of H and probability of T. So because this is each one on the right-hand side is a half times a half. All these are half times a half. So we are actually saying a quarter is a half times a half. So probability of simultaneous occurrence of those sample points is a product of their probabilities. The probability of simultaneous occurrence of those sample points is actually the product of the sample points. This is as a consequence of independence. So that's why I'm saying here, tosses of a coin are independent. And we have put a fair coin or an unbiased coin. So this implies the tosses are independent. Let us even look at the case where the coin is biased. Biased coin. So when you talk of a biased coin, it's like when you toss a coin which is biased. It means either head or tail, as Scott say, they are not equally likely. One could be more chances of occurring than the other. So for the sake of argument, I've just said, okay, suppose probability of a head is 2/3, and probability of tail now will be 1/3. As opposed to for the fair one, it's a half. So this is a coin which is loaded in such a way that it is not fair, it's not balanced. Probably using different metals, you can design such a coin. So that when you toss, the heavier part will be landing on the floor, and the lighter part lands on top or up. Now, then you'll see that probability of head. If you multiply the probabilities, you see probability of head is 2/3 times 2/3, 4/9. We go to head tail. Probability of head is 2/3 and probability of tail is 1/3. You'll get here 2/9. Similarly for tail head, you'll get 2/9. And then you can see for tail, you get a third times a third, you get 1/9. And if you sum these probabilities, you can actually see they sum to 1. So this actually shows that as a consequence, this actually implies that actually the totals are also independent. However, the sum of points are not equally likely. So the sum of points being equally likely does not, so that we distinguish that when you talk of independence, it does not mean that the sum of points must be equally likely. They may not be equally likely, but the events can be independent. So this implies the totals are independent. However, the sum of points are not equally likely. So the concept of independence doesn't really say that the sum, because I've used this example here, when they are equally likely, it's to demonstrate that they are independent. Here, the sum of points are not equally likely, and they are still independent. So you can see in the sample space, in the sample space, when we envisage this kind of scenario, we are actually saying in the sample space, whereas all of them were having a quarter in this in A, you can see they'll be having different probabilities here. You can see for head will be having 4/9, head tail will be having 2/9, and also tail head 2/9, and tail will be having 1/9. This is a scenario where the sum of points are not equally likely, but they are but the tosses now. We're talking about the tosses. The experiment itself, when you are performing that experiment, those tosses are independent still. Now let us see. Next, define the events. We had defined these events earlier when we were dealing with collision probabilities. Next, define the events E1, E2, E3, comprising those sample points as shown for E1, for E2, for E3. Consider the collision probabilities. Probability of E1 given E2, probability of E1 given E3, probability of E2 given E3. Let us see now for the fair coin. I've defined some events. Then I want to see whether these events I've defined are independent or not. You get these events which I've defined. E1, E2, E3. Let us see whether they are independent or not. Let us see for the fair or the unbiased coin. Even you get probability of E1 and E2. If you check E1 and E2, E1 is inside E2. Which probability of E1 you get a quarter. We get probability of E1 given E2. You can just use even the reduced sample space of E2. You look for E1, you can see you will get a half. Or you can even use the original sample space. So you get it is a half. Look at this. Probability of E1 given E2 is a half. But probability of E1 is a quarter. So probability of E1 given E2 is not probability of E1.
You don't believe?
Meaning E1 and E2 are not independent.
Don't you
If you
believe?
look also probability of E1 dash E3, E1 is inside E3. So probability of E1 dash E3 probability of which is a quarter.
Okay.
If you get probability of E1 given E3, you can even use the reduced sample space. In E3, you look for E1, you have 1, then you get 1/3. Not again probability of E1. Again, E1 and E3 are not independent. You look the other case, E2 dash E3 is probability of E2 because E2 is inside E3. That's probability of E2. Look at probability of E2 is 2/4, so it's a half.
When you are done.
And if you look probability of E2 given E3, you get is 2/3, not probability of E2. So actually, these events we have defined here, they are not, these events we have defined, they are not independent. The events E1, E2, and E3 are not independent. They are not independent. Now, you look for the bias coin, same story. Whether the coin is fair or the coin is unbalanced, still you'll find that the events so defined are not independent. These events we have defined here are not independent, whether the coin is fair, whether the coin is biased. So we have found for the biased coin what those probabilities are, and then you'll find that probability of E1 given E2. We have found probability of E1, probability of E2, probability of E3 for the biased coin. You only need to look for those sample points. Like for HH was 4/9. If you come for E2 comprises HH and HT, you need to solve those probabilities. So you get 4/9 plus 4/9, you get 6/9, get 2/3. For E3, you'll be using 4/9, 2/9, 2/9, you get 8/9. Luckily, because actually those we are dealing with sample points. Sample points are always mutually exclusive. You just need to sum the probabilities. So we have found probability of E1, probability of E2, probability of 3. If we get collision probabilities, you can see for E1 given E2 is 2/3. Not probability of E1, which is 4/9. Also see for E1 given E3 is a half. Not probability of E1, which is 4/9. You see for E2 given E3 is 3/4. Using quotient probability, not to quotient probability of E3, which is 8/9. You see? So that's in both cases, whether it's fair and biased coin, they are not independent. So we'll find that you can see whatever we were defining for independence, they are not true. You find the probability of E1 given E2 is not probability of E1. Probability of E1 given E3 is not probability of E1. Probability of E2 given E3 is not probability of E2. Meaning E1 and E2 are not independent. E1 and E3 are not independent. E2 and E3 are not independent. So we can actually say in general, E1, E2, and E3 are not pairwise independent. E1, E2, and E3 are not pairwise independent. If E1 and E2 were independent, if E2 and E3 were independent, and if E1 and E3 were independent, we could be saying the three events are pairwise independent. But now we have seen pairwise, the three events are not independent. So we can say actually E1, E2, and E3 are not pairwise. Taken in twos, they are not independent. Now, when we are discussing this concept of independence, the contrary, when they are not, to negate independence, we are saying they are dependent. So where we have said the events are not independent, we are actually saying they are dependent. So in these events, which we have established that they are not independent, these E1, E2, E3, these events are dependent. So that example will lead us to define what we mean by pairwise independence in the general sense. Now I've used those three events. Of course, trivially, when you have only two events, you can only pair them once. Get it? When you have two events, you can only pair them once because there are two. If you have three, you can have three pairs. You can have three pairs like that. So we want to generalize. Suppose we have k events. So we want to define pairwise independence generally with reference to k events. K is now arbitrary. If k is 1, if k is 2, you have two events, so you can only pair them once. If k is 3, you'll have 3 combination 2, which is 3 pairs. If k is 4, you have 4 combination 2, which is 6. Like that. So as k increases, you can generate so many pairs accordingly. So events E1, E2 up to EK in a sample space. So here this assume also events that our K here is finite, of course. You can count them. I say to be pairwise independent, even only if. So these are two-way statement. If this if this expression is true, that probability of EI dash EJ is the product of the probabilities, then you can say they are pairwise independent, and should be for all I not equals to J and I and J running from 1 to K. So it means all possible pairs. When we write this in mathematics, we mean all cases when I is not equals to J and I and J running from 1 to K, we are actually saying all possible pairs. With actually there will be how many? There will be K combination 2 possible pairs when you have got K events. Also, when you see if and only if means it is two-way. So when you want to define pairwise independent events, then you say this is true. And in case you establish that this is true, then you can deduce that the events are pairwise independent. So it is two-way. So we have defined that if they are independent, if this expression is true, and conversely, if this expression you can define independent events when you want to prove for independent events this expression to show. So we have to the independent if this is true. But if this is true also, then you can deduce independence. So when you want to prove independence, what you're actually saying, show this. The way we have used for two events, because we have defined that if E1 and E2 are independent, it is the product. That's why when you wanted to prove that probability of E1 complement and E2, when you wanted to prove that E1 complement and E2 are independent, we had to show that the probability of the induction is the product. So these things actually come from the definition. So when we are saying we prove this, it says by the definition. So we are saying they are K. So we are actually saying when you want to prove pairwise independence, you have to check K combination 2 conditions. So when K is large, there will be very many conditions to check. You can see when K is 2, it's only one condition. What do we use to define independent events of independence of two events? When K is 3, there are 3 conditions. Like that example it was illustrating. This example illustrating, we are doing 3 events. So there are 3 the ones who are checking. So these are the ones to check. So for 3 events, this must be true for them to be pairwise independent. So that's why I'm saying trivially, you need to go pairwise for K equals 2. It doesn't really make much sense because there's only one pair. So you just say they're independent. You don't say pairwise. If they are 4, they are actually 6. These are the 6 we are talking about. They have to be true. These are not means pairwise independence for the 4 events E1, E2, E3, E4. You can have 6 possible pairs. So the probability of the spontaneous occurrence of any row of them should be the product of their probabilities. So the way we write in mathematics, so when we have this for K equals 2, we have this. For K equals 3, we have this. For K equals to 4, we have this. So you can imagine if K was 5, combination 2, there'll be very more. But we write things in mathematics in a compact form. So when we write like this, we have taken care of all those cases. We don't have to enlist them. We know this takes care. So when you say, even for this scenario of K equals to 3, when you say probability of EI dash EJ, probability of EI, the probability of EJ for all I not equals to J. You see, you can see what those subscripts are. I not equals to J are these ones. 1 and 2, 1 and 3, 2 or 3, 2 and 3. Those are I not equals to J. For all of them, running from I and J, running from 2 to 3. You see 1, 2, 3. So they are actually compactly here. So even these 4 are compactly here. Even 5, they are here. All of them are here. for any arbitrary number of k events. This is the definition. This takes us now to define what we call mutual independence. When we talk of mutual independence, sometimes we call it complete independence. Some books also call it total independence. Now, when we talk of independence, we are not, we see pairwise talks only of two at a time. But when you talk of mutual independence, we are not only considering two at a time. We can also have them in threes. We can have them in fours and so forth, depending on the size of K. So we want to define mutual independence or complete independence. So events E1, E2 up to EK in a sample space are said to be mutually or completely independent, even only if for L equals to 2, 3 up to K. Look at that. We are saying probability of the intersection I equals to 1 to L. You can see how my L is varying. My L is varying. My L is varying from 2 to K. Meaning, when you have them in twos, when you have them in threes and fours, like that until all of them. So you can see in this product, the upper limit is varying so that you capture all possible combinations. You can have them in twos, that means in pairs, in threes, up to when L is case, that means you have all of them. So this is kind of stronger. This the kind of independence is stronger than the pairwise. That's why it's called complete independence or mutual independence. That's why when you are using the term mutual, when you are talking about mutually exclusive events, you are saying no two of them can occur together, no three of them can occur together. I have to say not all of them occur together. And for that one, it suffices that when no two of them can occur together, it will likely mean that when they are even in threes, in four, they will not occur together. It will likely mean also not all of them will occur together. So when you are talking about mutual, you are talking so in its entirety. Now, you can actually see that we are actually using that definition of independence. That's why probability of intersection is product of the probabilities. The events in question here, look at the events. The event is E, the subscript here is JI. J as a subscript I. So the first event we are talking about here is EJ1. And then the second one is EJ2 up to EJL. You see? You can see here I have how many events there? I have L events. And that L is changing from 2, 3 up to when you have all of them. So we are saying whatever number of events, the probability of simultaneous occurrence of them should be just the product of their probabilities. You can see? So it's actually that idea of independence. But we have considered all possible groupings from 2s, 3, 4s up to all of them. So you can actually say, these indices here we are having here, J1 up, J2 up to JL represent any L indices. They are actually L of them. J1, J2 up to JL, they are L of them. That's why you say I equals 1 to L. They are actually, and represent any L indices. You know? So when you are having the indices I'm talking about here, we are having 1, 2 up to K. But you are picking L of them, any of them. And that L is 2, 3 up to K. So when you say, it's like for instance, if you had say, so when you pick, you have to take your L to be 2. You see, you are putting them in twos. When you take your L equals 3, you are putting them in 3. And you can have various possibilities as we have seen when you put them in threes, what the number of conditions are. When you have L equals 3, you have all of them. Actually, E1, E2 up to EK. Now, so we are actually saying here, there are how many conditions to check here? Because there are K events, you can put them in how many? I ranging from 2 to k. You can have them in 2s, in 3s, up to all of them. So you'll have how many ways? Exactly k coefficient I running from 2 to k. But mathematically, this can be simplified as summation of k coefficient I running from 0 to k. But you see here, I don't have I equals to 1 and I equals 0. Then I must subtract. I must subtract because I'm adding k coefficient I. Let me start from 0 to k. Then I subtract what I don't have. I don't have for I equals to 1. So subtract k coefficient 1. I also don't have for I equals 0. Subtract k coefficient 0. And formally, if you know, we had demonstrated that this kind of summation of combinations is actually 2 raised to k using binomial theorem or binomial expansion. It is 2 raised to k. But k coefficient 1 is just k, and k coefficient 0 is 1. So this is the number of when you have got k events. The number of conditions to check for mutual independence are 2 power k minus k minus 1. 2 power k minus k minus 1. These are the conditions. So these are the conditions to check. 2 power k minus k minus 1 conditions to check. And for those k events to be mutual, all those conditions must satisfy this. The probability of simultaneous occurrence of events is the product of their probabilities for all those conditions. Let us see for k equals 3 because we have that example here. For k equals 3, they are actually 2 cubed minus 3 minus 1. They are actually 4 conditions. And you can actually see what those conditions are. In the pairs, we have already seen that when you have 3 there, 3 conditions. When you have 3 events, there are 3 conditions. The one we checked up there. And then for all of them, 1 condition. That's why we are saying there are 4 conditions. So what you are saying there are 4, these are the ones we are talking about. In the pairs and all. Because when you have 3, you can only have them in pairs, and then when you have all of them, it's just once. Just once. And actually, we are actually saying that is this was actually the idea of pairwise independent. That means they are actually pairwise independent. They must satisfy this with the 3 conditions. We are saying for all I not equals j, I and j running from 1 to 3, then we have all these conditions here we had listed here for k equals to 3, like for the pairwise. For the pairwise, where they are actually these ones. Yeah. These are the 3 conditions which we had expressed like that. So there are these 3. So there are those 3 now, and then all. So there are those, these are the 3 are here, and the last one is this one, when we have all of them. There's a 3 plus 1, 4 conditions. So for k equals to 4, they'll be in the pairs we see there are 6. 4 coefficient 2, there are 6. In triples, when you put them in 3s, 4 coefficient 3, they'll be 4. And then when you have all of them, all of them, you will have 1 case. 6 plus 4 plus 1 is 11, which is actually 2 raised to 4, which is actually 2 raised to 4 minus 4 minus 1, which is 11. These are the ones listed here. So if you are to list, you have to list 11 of them and check that the probability of simultaneous occurrence of the events is the product of their probabilities. So you can actually see as k becomes large, there are very many conditions. Yeah? Yeah? 2 raised to k minus 1. Now, so the one thing you have noted here is that when we are talking about mutual independence, because we're also putting them in pairs, it means events which are mutually independent are also pairwise independent. So mutually independent events are pairwise independent. However, pairwise independent events are not necessarily mutually independent. So once you have established, if you have established that events are mutually independent, then you know for sure that they are pairwise independent. But if you have established that the events are pairwise independent, not necessarily they will not necessarily be mutually independent. They might be pairwise independent, but not mutually. But if they are mutually independent, definitely they'll be pairwise because pairwise is one of the conditions. Hmm? These in pairs is actually for pairwise. These six are for pairwise. These three for three events for pairwise. Hmm? So the idea of independence is or pairwise is actually nested inside the mutual independence. Now, remark number two. We have been discussing what we call statistical independence, which sometimes we just translate it to independence. So statistical independence implies complete independence. So when we just mention independence without qualifying it, inherently we actually mean complete independence, not the pairwise. So statistical independence implies complete independence. That is, the events are mutually independent. So most of the time, when you read even some books, the moment you just hear them talk about independence, they're actually making reference to mutual independence, not the pairwise. Third, as I stressed this when I was starting, statistical independence is independence in the statistical sense. I want to use an example to demonstrate that events can be pairwise independent but not mutually independent. Consider the sample space comprising these four sample points using our notation for sample points E1, E2, E3, E4, and assume EIs are equally likely. So assume they are equally, so it means each one will have probability of a quarter. And then define the events. Call E1, event E1 to comprise sample point E1 and E4, event E2 to comprise sample point E2 and E4, and event E3 to comprise sample point E3 and E4. Remember our notation. When I'm talking about event, you can see I'm using notation of uppercase E. When I'm using sample point, I'm using lowercase e. Remember that notation which we started with. So we know probability of this each of these sample points is a quarter, what they are equally likely. Now, if you want to get probability of each of these events, use the classical definition. Each one of them has 2. So 2/4 is a half. So for each one of them, again, each one has a half. So you can actually see that probably, and if you check the intersection of any 2 of them, you can see E1 intersection E2 will have E4. E2 intersection E3 has E4. It's a singleton sample point, only one sample point, and then you can also E1 and E3. The intersection will only have E4. Just it's actually simple events. The intersections are actually simple events. It's actually a simple event comprising the sample point E4. So probability of EI is actually a half. I equals to 1 to 3. Each one has probability of a half. So you can actually see that probability of the intersection is probability of the simple event, E4, which is a quarter. And probability of EI is a half. So you can actually see that a quarter is actually a half times a half. For all I not equals to j, I and j running from 1 to 3. I and j taking 1, 2, and 3. So you can actually see it satisfies that condition of pairwise independence, meaning the 3 events so defined here are actually pairwise independent. Those are the 3 conditions. But now if we want to check mutual independence, we have to check now the 4th condition, all of them. E1, E2, E3. And if you intersect the three events, it will also be having only the E4, the sample point E4. So it's not a simple event. So probability of E1 dash E2 dash E3 is probability of the simple event E4, which is a quarter. But if you multiply the probabilities of E1, of E2, and of E3, of course, each one is a half, a half, a half. So half times half times half, 1 over 8. So you can see probability of the intersection of the three events is 1 over 8. I mean, the probability of the intersection of the three events is a quarter. Sorry. Probability of the intersection of the three events is a quarter. And the probability of the product of those events, probability of those events is 1 over 8. So probability of intersection, probability of E1, intersection E2, intersection E3 is not equals to the product of the probabilities. So the fourth condition for mutual independence is not satisfied. But the three conditions for pairwise independence are satisfied. Meaning these three events we have defined here are pairwise independent, but they are not mutually independent, or they are not completely independent. So these are an early example of events which are pairwise independent, but not mutually independent. But if events are mutually independent, you don't have to check whether they are pairwise independent. They will be, because that condition of pairwise independence is actually nested in the definition of mutual independence. Now, I want to leave this as an exercise. You'll have to do it. It says, consider an experiment of tossing or throwing a fair die twice. Consider an experiment. You can say toss, you can say throw a fair die. The die also is fair. So when you draw it, the probability of a face, there are 6 faces showing up, is 1 over 6. And then define these three events. E1, the first toss shows an even number. So out of 1, 2, 3, 4, 5, 6, you know which number is even. E2, the second toss shows an odd number. You know which number is odd when you have 1, 2, 3, 4, 5, 6. But that is the second toss. Then E3, the two tosses show both odd or both even numbers. That is event number 3. The two tosses show both odd or even, or both odd or both even. You know. So the first toss, if it is odd, the second toss should be odd. If the first toss is even, the second toss should be even. You have defined those events. So generate the sum of points in the sample space. Generate the sum of points in the sample space. What is die is tossed twice. When you toss a die once in the sample space, there are only 6 sample points. So when you toss it twice in the sample space, there are 36 sample points. And because the die is fair, the probability of each sample point there, remember, because the die is fair, each sample point, each of those 36 sample points are equally likely. So each one will have a probability of 1 over 36. Now, with these events defined as indicated, show that the events E1, E2, and E3 are pairwise but not mutually independent. So you need to do that exercise. First, you start by enlisting all the sample points in sample space. And actually, that sample space is actually that you have it as an array, 6 by 6. That's from 1, 1 up to 6, 6 sample points there. Comprising 36 sample points. So you know what to check. Now, what we have done so far on probability and its properties, we now have enough tools or the language that we can use in the study of random variables. And what is important about random variables is that you see in probability we start by introducing events. That means you have performed an experiment. You have performed a random experiment. Then there are events. Then you want to check what are the chances of an event so defined that it occurs. Then you bring in the idea of probability. But to make it more realistic is that suppose you want to study some characteristic of or of a certain population, you know. So we have to bring in that idea of probability here also, which also would relate to our sample space of that random experiment you have performed. And more importantly, this random variable has to do with what you want to study in a population. Some characteristic of a given population you want to study that characteristic. So we are going to define a random what you call a random variable. We can be any characteristic you want to study in the population. Exactly that characteristic you are referring to is you will be able to take measurements on that characteristic. You will be able to measure. What are you measuring in that population? And bringing in uncertainty, bringing in now the idea, the concept of uncertainty in all that what you are doing with that population. You know, because even when you are taking measurements, you cannot measure them to its accuracy with certainty. You know, there'll be some randomness. So we're now to introduce and what we have learned now on probability, like up to conditional independence, will be now also brought on board when studying random variables. We shall also be talking, and then later when we have reached after we have defined events again in terms of a random variable, we are able to use the same ideas we have gone through. So we settled down there very fast. So the random variables. So random variables are used in defining certain probability functions that make it both convenient and easy to compute probabilities of various events. So the whole idea is our interest also is to be able to compute probabilities of various events, and these events now they'll be defined in terms of a random variable. It to relate to the sample points in the sample space, but in terms of the random variable. So we shall define an event in terms of the random variable and link it to the sample point in sample space. So a formal definition of a random variable. A random variable, which in short, might define me writing in short all the time, like RV, I use it to denote random variable. So a random variable X. Now, notation. When writing a random variable, we use uppercase. That's why I write so. When you can see this X is capital X, not small x. So a random variable X is a real valued function defined on a sample space S. That is, so functionally, what it actually means is that, when you are saying real valued, it means as a function, we're now saying we have a function denoted by this x, which is a random variable, mapping the elements of S, which are sample points, or generally later on, which are also events, into real numbers. That's why it is called, you were saying, this real value. That means this mapping them into real numbers or transforming them into real numbers. Geometrically, this is what I'm saying here. So we have a sample point. Let me use the case of a sample point E in S. And then there is a mapping or a transformation. So that function transforms the number E into a real number. So X of E is now a real number. That's why. So this is R. X of E is real. That means it's in R. That's why we are saying it maps elements of S to R, to real numbers. That's why I say it's real valued. So we are actually saying, from the knowledge of functions, we are saying the domain of a random variable is a sample space. The domain of a random variable is a sample space. And what we call the range, sometimes also we call the codomain. So the domain of a random variable is a sample space, and the codomain is the set of real numbers. So simply put, the function x transforms, or you can use a simple word, maps. When introducing functions, we talk about mapping. But later on, it's taken to more elegant terms like transforms. So the function x transforms the elements of S into real numbers. Is what that says. So specifically, the range is a certain subset of R. So when you are saying into real numbers, you are not saying the whole set of real numbers. The codomain can just be a subset of R, but still they are real numbers. So it's not the entire real set. We are just saying they are real numbers. Even if it is a finite interval, a very small finite interval, it is still they are real numbers. So the idea of functions is also important here, because we know for when we talk of functions, we can have 2 points in the sample space being mapped into the same point in the range. But you cannot have 1 point being mapped to different points in the range. You cannot have 1 point in sample space or in the domain being mapped to 2 different sample points, to 2 different points, or I mean two different values in the range. That cannot be a function. So it is the same idea, because we are now treating our random variable as a function, so we cannot break those rules of functions. So we are actually saying 2 or more different sample points might give the same sample value of this. So 2 different points or 3 different points in the sample space can actually be mapped to the same point, to the same real number. So that is a property of a function. But but you cannot have one sample point being mapped into different values in R. That's not a function. Now, but 2 different numbers in the range cannot be assigned with the same sample point. That's what I'm saying. 2 different values in the range cannot be assigned with the same sample point. So there's no way you can have we can have one sample point being mapped to different values, because there's going to be what now in the range. You say this one goes to that one, also goes to this one. That's not a function. Now, the range comprises possible values of the random variable. So what we are calling the range, later on we shall be talking about possible values of the random variable. When I said you want to study a certain characteristic in a population, and you are going to take measurement, what are the possible values of that characteristic? When you are going to take measurement, what are the possible values we expect? So the range comprises possible values of the random variable. So later on, you'll be hearing us talking about what are the possible values of the random variable. That will also help us in defining distributions of this random variable. Now, for a point E in S, this is a sample point. For a point E, this is basically a sample point E in S. This is lowercase e in S. These are sample points. X of E is the value of the random variables. So what you are actually saying here geometrically, this X of E is what you are now calling the value of the random variable. The number it takes. So after you have done your measurement, this is what you'll have as a measurement. After you have done with your characteristic, this is the measurement you'll have. This will be a value. A tangible value. Now, XE is the value of the random variable. Now, this tradition, or what in terms of notation, which we should not violate. If you violate, the whole thing breaks down and doesn't make sense. It is customary to use uppercase, which some people like calling them capital letters. X, Y, Z, these are, you can see these are uppercase, to denote random variables. So this is why when I was defining random variable, I'm intentionally using a capital X. So later on, I see you writing a random variable using small x, and I say, no, you have not been with me, and I will disown you. Now, and the corresponding lowercase, some people like calling them small letters. You can see again, X, Y, Z. These are the corresponding small. So when we write X capital, you can see it has to be, you know how you write a capital letter. This is X, this is lowercase. The Y capital, small y. Z, we write Z, and they might look alike, but when you are writing the value, you actually make it small. We usually don't use the other Z, which we write like almost like a 3. No, we use the Z but small in size. Because we shall be using these notations. ETC. So whichever, you don't restrict yourselves to now that there is Y, X, Y, Z. Later on, you can define a random variable U. A random variable what? Anything. They must be capital. The moment you just hear the word random variable, write it as capital. And then the value assumed by the random variable, write it small. A random variable is said to be discrete if it assumes or takes. So that I'm will be using this, it takes these values or assumes these values, same story. If it assumes or takes only a finite. That's why I brought in this idea of finite or countably infinite before. A random variable is said to be discrete if it assumes or takes only a finite or countably infinite. So a finite means, you know what I mean by finite? Or countably infinite, we are discussing number of values on the real line. You see, like it can be infinite but countable. Like 1, 2, 3 up to infinity. It's infinite but countable. That is discrete. Or if we take, say, 1, 2, 3 up to some finite number, say k, where k is finite, that is finite. But okay, so 1, 2, 3 up to infinity is countable but infinite. So all those, yes, so that we would refer to random variables which are discrete. A random variable is said to be continuous if it assumes any value in an interval of the real line. So that's where they differ now. You can actually see that a discrete random variable takes particular values, but a continuous random variable takes values in an interval. So a continuous random variable does not take particular values. It only takes values in an interval of the real line. Any interval. And because the real line itself is uncountable, and even any interval of the real line is uncountable. So we are actually saying a continuous random variable assumes an uncountable number of values. Even if you have the interval 0, 1, it's still uncountable. Even if you have a finite interval, say AB, where A is less than B, it is the interval is finite, but the number of values there is infinite. So it is still, that interval is uncountable. So that is where a discrete random variable and a continuous random variable differ. And you'll see later on when we define probability distributions, there is what we call the support. The support actually talks about the values assumed by the random variable. That is why you'll find that the support of a discrete random variable will be defined either by finite or infinite number of values on the real line. That is what the random variable takes. And if we are defining a continuous, a probability distribution of a continuous random variable, yeah, you'll find that its support will actually be an interval. So you'll find that for all random variables which are continuous, the support of the distribution will actually be intervals. It can be a finite interval, it can be infinite interval. That means say up to infinity or even up to minus infinity. Thus, a coordinate random variable assumes a countable number of values. In particular, R is uncountably infinite. So you might even find a random variable which takes values in R. And that means takes values from minus infinity to infinity. And you shall see examples of those distributions which takes values from minus infinity to infinity. That is exactly R. It's a coordinate random variable. Like the normal takes minus infinity to infinity. A T minus infinity to infinity. There are those which take in R plus, like the gamma, 0 to infinity. You can also have, say, beta distribution, which will take values in the interval 0, 1. Because it's still continuous. That interval is uncountable. Now I want to bring the idea of events. You know, we discuss events by looking at some points, and then we say, okay, when you perform an experiment, these are the possible outcomes. Then you define an event of interest. Right? And that event is actually described by the you have that description. What do you mean by that event? And then you enlist the sample points which satisfies that description. The event, meaning the event you have defined in simple language. So we want to see how we can define events so that we are able now to bring in the idea of probability, because we already know how to deal with probability for events in a sample space. We want to bring in the idea of probability now on this random variable. So first and foremost, events defined by a random variable. Consider a random variable x and a fixed real number x. You can notice a difference here. This is a random variable uppercase. You can see this is very deliberate way, and then this is and a fixed real number small x. You can see fixed real number. This is a real number, the way you know real numbers. Now we define the event. This is an event now. The event, put the in brackets. People also call it parentheses. I think these are parentheses, to be more specific. And this event is described as the random variable x is equal to small x. What does it mean? We are actually saying the random variable assumes the value x, because x is a fixed real number. The random variable x assumes the value x. Oh, it's even here. Oh, wow, it's here. It's here. That's what I mean. It's here. Oh, I don't know. I don't know if it should be discrete. If it assumes text, is it? This is the language I'm using. Assumes or text. Because it only a finite number. That's when you're describing discrete. So it assumes or text. Then we come here. Okay, again, random variable is said to be correct if it assumes or takes any value in an interval. So it's about assuming or taking is just the same story. Now you come here. We only define that we have defined an event that the random variable x takes or assumes. I'll be using the two words interchangeably, assumes or takes. So the random variable x takes or assumes the real number x. You see, everything here is x, but you see the notation is important. They are two different things. So this is something which is taking a value. So when I was referring to you are taking measurements of certain characteristic in a population. So after you have taken your measurement, now you are saying, this is the value. This is the value you have recorded. So this event will be defined now as follows. This event is defined as, so I've already described what that is. This is what essentially it means. We are saying that this x, we have defined it as a function, mapping the elements of S, the sample space, into real numbers. This event is how we now write here as this the event on the right-hand side we are defining as a set in terms of the sample points. This event would be equivalent to what we have on the right-hand side. And the event on the right-hand side says it will comprise sample point E such that x of E is x. It will comprise those sample points in S such that x of E will take the value x in the range or in the codomain. So that's how we have now defined an event in terms of a random variable. We have already dealt with this. We have been defining events in terms of sample points and computing their probabilities in various ways. But now we can see how we define an event in terms of a random variable, what essentially it means. And we need to take cognizance of the fact that if events which are equivalent, because we are actually saying these two events are equivalent, it's just the same as this. They say the same thing. That means they will also have equal probabilities. So we shall be moving the way we are computing probability in terms of sample points to computing probabilities in terms of events defined by a random variable. Now, in some situations, the outcome E of the sample space, what we are calling the outcome, is actually the sample point of the sample space, is already the numerical characteristic which you want to record. Sometimes you might find that in a sample space, the sample space actually comprise numbers, like tossing or throwing a die. The sample space we toss it once, it will comprise sample points 1, 2, 3, up to 6. Already you can see if in that random experiment, those are the things of interest. You find that what actually the E are only numbers. In this generality, E, the sample points need not be a number, depending on what is of interest. Like when you were saying you toss a coin, head and tail, those are not numbers. But when you toss a die, 1, 2, 3, 4, 5, those are numbers. So it depends. That's what I'm saying. In some situations, the outcome E of the sample space is only the numerical character which you want to record. That was of interest is now that your measurement already is a number. So in this case, we simply take x of E is E. So we are actually saying x of E is basically E. It's already a number. In such situations, we call it the random variable. We are taking what we call the identity function. When you have a function, say f of x is equals x, is identity. 1 is mapped to 1. 2 is mapped to 2. Identity function. So we are saying x of E just E. So when you're having, when you say x of 1, when you roll a die, it just be 1. Identity function. Now, and you shall see when you look at the various examples. Similarly, for fixed numbers, suppose now we fix some numbers, we indicated that this small x is fixed. Similarly, suppose we now have, so I want to describe various events. Let us say our x is fixed, x1 is fixed, x2 is fixed. Those are numbers which are fixed. Okay? So that I'm able to describe various events. You see, we have this x is fixed. So I've described this event. If I have fixed x, I can also describe this event. X is fixed. You can see I'm saying x is equals to x. So get me very correctly when I say x is equals to x. But the random variable x is equals to the value x should be lowercase. So when I say x equals to x, not random variable equals random variable or small x equals small x. No. With that notation, I'm having that in mind. So you can see the way I've defined this event, similarly, I can define this event. Say x is less or equals to x. You are saying x is equals to. Suppose we want to define an event x is less or equals to x. Same story. You can look at the right hand side. It will comprise those are the points in S, such that x of E will be less or equals to x. So if we were to list that, if the sum of points in the defined by that event is a random variable, we will actually list them. Suppose I want to define this event. The random variable x is greater than small x. So it will comprise those sum of points in S such that x of P will be greater than x. Suppose I want to define this event here. That's why I was fixing also x1 and x2. For purpose I want to define this event. Suppose I say suppose the random variable is less or equals to x2. X2 is fixed fixed number, and x1 is a fixed number. So suppose it lies between x1 and x2. X2 inclusive, but x1 exclusive. Then I'll say that event comprises sum of points in S, so that x of E lies in that interval. And we have defined that event. Let us see how we move. So I'll use various examples, maybe, and we shall try to capture this. And in the process, also, we shall be seeing whether the random variable in question is discrete or continuous. If it is taking a finite number or countably infinite number of values, then we know it is discrete. If it is taking values in an interval, then we know it's continuous. Example number 1. And also in these examples, you know when I say you are, as a characteristic of interest you are studying, you are denoting it by a random variable x. It is what you can define. The scope is huge, depending on what you are studying and the context. It is very huge. It depends on your idea of where you are applying it, what you are interested in. As you perform your experiment, what do you want to measure? So let us look at these examples. Example number 1. Tossing a coin. Tossing a coin. And I've said under A once, under B twice. And let x be the number of 8. And let x, you can see I'm denoting by x capital. I'm now defining a random variable. And let x be the number of 8. See, I've defined my random variable. In my random experiment, I've defined my random variable. So let us look at A. A says you have tossed a coin once. This is a sample space, head or tail. Now we have defined our random variable. Let x be the number of 8s. So we want to transform these sample points in S into numbers. As by the definition of your random variable. Number of 8s. So let us transform H. X of H. X is a number of 8s. So on the sample point H, it's like you are counting how many 8s are there. So one X of H is 1 8. But when you go to X of T, there is no 8. T is not 8. So that is 0. So what you are saying, X takes or assumes small x. These are now the values, 0 and 1. Those are what you are calling the possible values of the random variable. The values it takes or assumes. So 0 and 1 are the possible values of x. No. So later on, when we talk of a probability distribution of x, that probability distribution will have the support of 0 and 1. One thing to note is that it's taking a finite number of values, 0 and 1. So x is discrete. So x is a discrete random variable. B says toss it twice. You are tossing a coin, but now twice. Sample space changes to this. 4 sample points. As by our definition again, x is the number of 8s. So when you go to sample point HH, you are counting the number of 8s. These are 2. So x, H, H, and the sample point 2. For HT and TH, 1. And for TT, 0. So the x can assume or take this value 0, 1, 2. So x again is a discrete random variable. The one I just mentioned about a few minutes ago, you can now see in the sample space in 1, these are not numbers, they are just symbols, but they have now been mapped to numbers, which basically you are saying they are real numbers. And when we come to talk about finite number or countably infinite number, for it to be discrete, it's actually taking particular values. Whereas if you go to number 2, you are tossing a die, you find that the sample space, the sample points are actually numbers. And probably you are interested in these numbers. So what you are recording as 2 is like your measurement. So we are talking, let x be the number that shows up. You see, then you are defining what is already there as a number. With the sample space, they are numbers. That's why this now when you are talking about the identity function. For that x of e is just e. And e is 1, 2, 3, 4, 5, 6. This is identity function. It's like you are mapping your number just to a number. In this case, we are actually saying e is just x. The value assumed by the random variable, x is just your e, the sample point. So when you talk of the post value of the random variable, x is just e, the sample point in S. Again, then here, it takes a finite number of values, x is discrete. X is a discrete random variable. Let us see number 3. A natural number is read at random in the interval. You see? You know what natural number is? 1, 2, 3, up to infinity. Those are natural numbers. So with a natural number, so it's the way you define a random variable. I'm defining here. A natural number is rated at random in the interval. A natural number is rated at random in the interval 0 to infinity, excluding 0, of course. Then these are natural numbers 1, 2, 3 up to infinity. These are samples. These are your sample space. Let x be the number selected. Suppose we define a random variable now. Let x be the number selected. You have defined a random variable now in that random experiment. This was a random experiment. You have now defined a random variable. Let x be the number selected. Then again, you find that x, you can see the sample in the sample space, there are numbers. So you can actually define an identity function. So you can actually have a random variable saying, let x be the number selected. So those are the numbers you'll be recording. Then x of e is just e, the identity function. Again, it takes a countably infinite number of values. They are infinite, but countable. So again, x is a discrete random variable. Look at 4. A real number is related at random in the closed interval AB, where a is less than b, so that you have an interval. Then you find that your sample space will comprise points, real numbers, which lie in that interval AB, that closed interval AB. Suppose I say, let x be the number selected. Then x of e is just x. And the number is in the interval. So it will be taking values in that interval. So because it is taking values in an interval, that x lies between a and b. In other words, it is taking values in an interval, not particular values as such. So this e is x means x lies in that interval. And if it takes 49 after x a continuous random variable. For example, 4 is giving us 1, 2, 3, they're all discrete. And also, this identity function identified, but they're all discrete. This was finite, this is countably infinite, this is now continuous. Continuous, of course, is uncountably infinite for continuous. That interval is actually is uncountable. Now, even though the interval is finite, because A and B are finite, the number of values in that interval are infinite. That's why we say that interval is uncountable. Let us look at 5. A real number is read at random in the interval 0 to infinity. Then, that is your sample space. Let x be the number selected, then x is a Korean random variable. So you can actually see for 4 is a finite interval, but still uncountably infinite. Here, the interval is not finite, but still uncountably infinite. So you can have an interval which is finite in the sense that A and B are finite, but the numbers in there is infinite. But here we have an interval which is not finite even. The numbers also there is infinite. So I'm bringing 4 and 5 so that you can have two cases which are actually different. In these examples, we recognize that actually examples 1 and 2, in examples 1 and 2, the range of x is finite. In examples 1 and 2, for tossing a coin and for tossing a die, we are saying in examples 1 and 2, the range of x is finite. That's why we were saying discrete. In examples 3, 4, and 6, the range of x is infinite. If you look at for 3, 4, in examples 3, 4, and 5, you look at 3, it's infinite, 4 infinite, 5 infinite. In examples 3, 4, and 5, the range of x is infinite. Moreover, in example 3, the range is countably infinite. That is why x is discrete. They are all infinite. For 3, 4, and 5, they are infinite. But specifically, in example 3, the range is countably infinite. That's why it is discrete. Whereas in examples 4 and 5, the range is countably infinite, meaning x is continuous for 4 and 5, even though all of them are infinite. Contrastingly, the interval in example 4 is finite. The AB is finite. But in example 5, it is infinite. So we are saying you can have a finite interval, but it's still actually countably infinite because the number of values there is countably infinite. Uncountably infinite. They are uncountably infinite. That's what you are talking about, continuous. So later on, when you go to distributions, one should be able to recognize whether you are dealing with a discrete probability distribution or a continuous probability. There are people who confuse the two. And it's very unfortunate when you see somebody writing a distribution which is continuous and putting the support to be discrete. Now, it makes everything very cumbersome. There'll be nothing to do there if you are not going to capture the support of a distribution correctly. Because suppose even you wanted to say to generate some random numbers from a distribution, you must know its support. Now, I have some important remarks here. These remarks are very important. Then we shall see how do we compute probabilities now, defined by random variable. Let's look at these remarks. The set of all values, let us call it Rx. X is a subscript. This is our random variable. Let us call it Rx. R is actually to denote the range with respect to the random variable X. You see, we had said we are mapping values to real numbers. And we have said generally, the range is not R in its entirety, it might be a subset. So the subset I'm referring to, I'm calling it Rx. This is the range for the random variable X, the codomain of the random variable X. Can actually be R itself. So the way we write R for real numbers, the way we use notation, even the way we write for natural numbers, whatever, the way we write, they usually have some form of, there's a name we use it in math, even in latex, to capture that. So we write in such a fashion. I believe you must be familiar with this. So we're actually what you're calling is a subset, and it can also be an improper subset, meaning the entire R. So the set of values Rx, which can be a subset of R, so these are real numbers, is sometimes called the range space. So what you are actually calling the range or the codomain of the random variable is also called the range space. Just to they are mapping elements of the sample space. Sometimes also we call that range the range space now. We are moving from sample space of the random experiment to range space. And these are values, which is a subset of R. So in a sense, we may consider Rx, the range space, as another sample space of some kind. Now you are moving from a random experiment to numbers. And you can see that when you define an event in terms of random variable, you are going back to the sample space, then you pick those sample points, and then you are move them now to numbers. So when you are in numbers now in R, it's like you are forming some kind of sample space in some form. So the original sample space, S, don't forget, corresponds to the possibly non-numerical. The fact the sample points are not necessarily numerical when you are in S. They can be just notations, the way you are saying, hey, tail, what. So the original sample space corresponds to the possibly non-numerical outcome. They can be numerical of the experiment. While Rx, which you are calling the range space, it is now the sample space associated with the random variable X, representing the numerical characteristic is now like the measurements now you are getting. You are corresponding the numerical characteristic which may be of interest. Now it depends on what you want to study. That is why if when in probability theory, most of the time we start from the random variable. Once we have once we have said this random variable takes these values, we may not even go back how the sample space, the original sample space looked like. We may not bother because already you have transformed. You are already at the range space, and you know the values it takes, and then the rest takes off from there. In fact, if x of e is e, the identity function, then you'll find that your Rx is actually S. That's why we are calling this range space is some kind of sample space. For the case of for example, drawing a die, S is Rx. The range space is just a sample space. Remark number 2. In studying random variables, now when we want to focus on random variables, in studying random variables, we are more concerned about the values of about the values X assumes than about its functional form. That's why we may not really bother how the sample space look like. We are more concerned with the values it takes. Hence, in many cases, we shall completely ignore the underlying sample space. So when the forecast is on a random variable, we can actually ignore the underlying sample space of the random experiment on which X may be defined. Because once we have established these are the possible of the random variables and the forecast is set in the random variable, then the blend can take off from there. Now, how do we compute probabilities defined, probabilities of events defined by a random variable? We already know how to compute probabilities with the events we are defining in terms of sample points, but already now we have actually defined events in terms of a random variable. So we have seen some equivalence between our events defined by a random variable and the sample points in the sample space. And because they are equivalent, we usually say in probability, equivalent events have equal probability. So first, we know that equivalent events have equal probabilities. For instance, remember, I'm now using even the events we are defined. You can exactly see these are the events we are defined earlier. The ones we have on the left-hand side here. And then they were equivalent these events we have on the right-hand side. And because they're equivalent, you can see I'm now saying they have equal probabilities. Those events have equal probabilities. So we will not be, so you'll find that once we know these probabilities in terms of the random variable, we may not actually bother to know how the sample space of the underlying random experiment look like, what were the sample points in them. It will not be of concern to us. So if we have captured the values assumed by the random variable, it will suffice to study that random variable. Let us see this example. Tossing a fair coin 3 times. Tossing a fair coin 3 times. As we know, there'll be 8 sample points, 2 raised to 3. There'll be 8 sample points. So, because the coin is fair, the sample points are equally likely. So when you want to get probability of the of events defined in this sample space, remember the classical definition. Now we have defined the random variable. Let X be the number of 8s. Then when you have X of H is 3, X of HHT and X of HTH, and the other one X of THH is 2. Let's like that.